Okay, let's get started. It's good. Okay, so we will continue the last few slides from last time, and then I'll switch to the topic for today, which is going to be on virtualization. Okay, but before I start, just a few announcements. There was a homework that I was supposed to give out on Monday, but I'm a little behind, so I'm going to hand this out today. Okay, so homework 1 will be out today. It will be due in a week from today. Okay, and I hope that there won't be any further delays, and we'll keep to the schedule that has been posted on the course webpage. Okay. The other announcement is the email I sent out, which is that there's going to be a makeup class this Friday, this time in this room. Okay, this is just to accommodate some future travel. Occasionally, I have an extra makeup class. This one is happening in advance of the missed class. So please take the time to come. It's going to be a regular lecture. Everything on the lecture is part of a test and whatnot, so it's not optional. Okay. If you have actual conflicts and are unable to come for a genuine reason, class is recorded, so that's not a problem. But I would strongly urge you to come and participate in class. Okay. So with that, let's get started with what we were talking about last time was distributed scheduling. Yes, question.
Sorry, quick question.
Sure.
The class on Friday, will that material also be on the quiz for this week?
Oh, the question is the class on Friday, will that be on the quiz? No, it will not be on the quiz, because the quiz will come out at the same time as the lecture. So it will be for the next week. Okay. All right. So just continuing from where we left off last time, we were talking about distributed scheduling, which is how do you schedule jobs across a cluster of machines. And we saw that there are many scenarios where even contemplating distributed scheduling does not provide any benefits, because either there is no reason to move the job or there is nowhere to move the job. Okay? But when the system as a whole is moderately utilized, we find that there is some benefit in doing so. We looked at several policies to performing distributed scheduling, from sender initiated to receiver initiated to mixed policies which are adaptive. And then we looked at some case studies, and that's where we left off last time. So we are talking about Condor, okay, which I said is another system that allows us to take a set of machines that are on people's desks and use the idle cycles on those machines to schedule batch computation or any other job that the user needs more cycles than they have on their local machine. Okay. So it uses idle cycles on workstations in a LAN environment. It can run large batch jobs, simulations, all of that. Whenever the user does not use their machine, the screensaver will activate. It will contact the Condor server, ask for work, and then it will start running those processes. When the user comes back, the machine is handed back to the user. The job is suspended. So it has the same philosophy as Sprite in terms of the user owns their machine. So you only use the machine cycles when they are not actively using their machine. Okay? Same philosophy holds. Okay? So Condor has some support for process migration. If it's the same operating system across machines, you can enable process migration. It does need a file system where you can save the state of the process and resume execution elsewhere. Okay? And I said that similar policies are now used in cluster schedulers, which are not necessarily harvesting idle cycles. There's just a pool of machines to which users can submit jobs. Okay? So there's a master node that's going to decide which job gets scheduled where. When the job finishes, then the next job in the queue is going to get scheduled on one of those machines. Okay? So there are a number of these examples, such as Sun Grid Engine. There's the Slurm scheduler. That's the one actually that is used in the clusters here. If you have used any of the large clusters in this environment, you would know the Slurm scheduler. It's a flexible scheduler. It has many different policies. You can have multiple queues and whatnot. It allows you to decide how to schedule across queues and so on. So, but it has the same philosophy. There's a master node that is going to distribute jobs that users submit to a pool of machines in the cluster. Okay, so that's how you do distributed scheduling. Okay. The last case study is on replicated web servers, and we will get to replicated or what are called clustered web servers later on in this course. But for now, since we are talking about distributed scheduling, you should know that when you have a large website where the website runs on more than one machine, you typically have a dispatcher node or a master node. So HTTP requests come to the master. They are queued up, and the master is going to then assign those requests to one of the other machines that actually service requests. Okay? So it has essentially this master slave configuration. So your master node essentially runs a distributed request scheduler for each HTTP request. Okay? There are many different policies that you can use, which could be things like round robin or least loaded and so on. Okay? And then there are other considerations here where you can do load balancing across these nodes on a session basis rather than a user request basis. A session is essentially all the requests that a single user performs. Okay? Typically, if your application has state that it maintains, say you are shopping at an online store and you put something into a cart, an online shopping cart, that state that now the application is maintained for the user. Okay? If that state is stored in memory of one machine in the cluster, if your next request goes to some other machine, it won't be able to do the right thing. Okay? So you might have to ensure that all requests from a user within a session are mapped onto the same request and so on. So there are sophisticated policies that decide how the scheduler is actually going to map requests to machines and whatnot. So we'll come back to this when we talk about the World Wide Web. All you need to know now is that some form of distributed scheduling also exists on clustered web servers and whatnot. Okay? So with that, I am going to now switch gears. I'll pause for any questions, if any, on what I said. Otherwise, we will now move on to a new topic, okay, which is virtualization. Okay, again, we have 3 parts to the lecture. I'll introduce what is virtualization. Okay. The next module is going to talk about how we implement virtualization on the processor or on the CPU. The last part says how do you use these ideas to virtualize other resources like the memory, the disk and whatnot. Okay, so that's basically what we are going to look at today. Okay, so let me introduce what is virtualization. Okay, so here is a very simple definition of virtualization. Okay, so it's essentially the use of one interface that a computer provides to emulate a second interface. Okay, so essentially it says you use or extend an existing interface to mimic the behavior of another system. Okay? So let me give you a little bit of history as to why virtualization was put in place to begin with. Okay, so virtualization is actually a very old technology, although it has become popular in recent years in the cloud or in servers and so on. It dates back to the 1970s. Okay? So this is basically back in the mainframe era. Okay? So companies like IBM would sell these very large computers called mainframes. They cost millions of dollars to buy. Okay? And large corporations would buy them and essentially run all of their computations on those machines. Okay? Now suppose you are a mainframe customer and you spent a lot of money buying a mainframe, and maybe it is now many years old and it's time to buy a new machine. Okay? So you go back to a vendor, typically maybe it's IBM, and say I would like to purchase a new machine, and then IBM would tell you, oh, we have a much better machine than what you bought 5 or 10 years ago. It's much more powerful, it has much faster processor and whatnot. And then they would say, by the way, since the processor has changed, the operating system changed, none of your programs that run on your current machine will run anymore because everything has changed. Okay? So now if you're a customer that is going to invest a lot of money to buy a machine, and nothing that is running on your current machine will actually run on this machine because the processor family changed, the operating system changed, all the interfaces changed, that doesn't make you happy necessarily, right? So that's not a good story to tell to your customers. So, but in those days, technology evolved so quickly that every few years there were new innovations that did not let your machine hardware be backward compatible. So you had to actually keep up with the technology and put out new features that did not ensure backward compatibility. So what IBM engineers came up with was this idea of virtualization, which said, let there be a new machine, let it run a new CPU which doesn't actually have the same instruction set as the previous one. Let the operating system be different. It doesn't matter. Let's run a software layer on top of it, which is going to emulate the old machine. Okay? So that software layer, all it is doing is it's providing the exact same OS interface as the old generation machine. Okay? So this provides backward compatibility. If you have old applications, okay, you just run this on the software layer. All of its calls that it makes to the OS or the libraries are going to be supported by this software layer. Okay, and it will run unmodified. You don't have to change anything at all. Okay. This software layer is essentially giving the illusion to this old application that it's running on the same hardware it ran before. Okay. The application doesn't know it's actually running on a completely different hardware now. It looks exactly the same to that application. Okay. Now you could also write new applications from scratch, okay, or develop new applications, and they would take advantage of the modern features that this new machine provides. Okay. And those would run on the native operating system, okay, not on the software layer that's emulating an old interface. Okay. So this is essentially how virtualization came about. So now you could say, I can sell you a machine. It's going to cost you many more millions of dollars, but everything that runs on your old machine will run exactly the same. And if should you wish to write new application, there are now new features that will make it even better for you to develop applications. Okay, your question, yes.
Does the mainframe machines at that time has an operating system?
Okay, question, the mainframe machines have operating system. They did indeed have an operating system. It was called OS 360, and there are many generations of it. Yes. Early versions of Unix actually came out from those operating systems. Okay. So that's the history, a short history lesson into virtualization. So here's a picture of what this would look like. So this is your machine A. This is in our example, the old machine. It has some hardware and software on that machine. Okay, and there is an interface that your operating system or the libraries that you use to program provide to your application. That is what we'll call interface A. Okay. So here is a new machine. Okay, it has now hardware and OS, which we'll call hardware for machine B, which looks nothing like the old one, which doesn't look like the one on A. So nothing that would run on A would run here, unmodified. Okay. So this machine is going to now expose interface B, which is actually different from interface A. Okay. The system calls would have changed, maybe the libraries have changed and all of that. Okay. Now on top of that interface B, we have the software layer, which is our virtualization layer. That is essentially using interface B to mimic interface A. Okay. Essentially all the calls that are supported by interface A essentially are now wrappers that are now re-implemented internally using interface B. Okay. So they do the same thing, but now you basically expose interface A and re-implement those calls using the native interface. That's what your virtualization layer has done. So your old program that ran on A will actually run on that same interface A, which is now mimicked by your virtualization layer. Okay. So that in essence is what all virtualization technologies do. They use the native interface provided by the machine to provide an arbitrary new interface or an old interface, whatever you are trying to virtualize. Okay. So it's essentially using a software layer to take one interface to provide a second interface to the application. Okay. Yes, question.
So what part of that image is the actual software layer?
What part of the image is the software layer? So the one between A and B is your software layer. Okay, there's an OS underneath B, and then there's the actual machine hardware underneath interface B. Okay, but the part between A and B is your virtualization layer. Okay, that's implemented in software. Okay. Okay. So now this is a very broad and general definition of virtualization. So now if you want to make this more concrete, you should ask what interfaces can we actually emulate or mimic. Okay. And the answer is there are many different layers of interfaces you can choose to emulate, and depending on what layer you choose to emulate, you will get different types of virtualization. There's no one thing that is virtualization. There are different levels of layers of virtualization. Okay. So if you actually virtualize or mimic the hardware instruction, the CPU instructions, okay, if you mimic one CPU instruction using another, you get what is called hardware virtualization. You can essentially mimic one CPU in software using the native CPU. You can make it look like an Intel machine is actually some other machine using emulation. Okay. Here the CPU is the one that is actually being mimicked using the native CPU. That's called hardware virtualization. Okay. Now you could actually mimic the OS interface, not the hardware interface. In this case, you are mimicking system calls. Okay. So you can take the system calls of one operating system and emulate the system call of a completely different operating system. Okay. So you can actually re-implement the Windows interface, okay, on Linux. Okay. So you can actually run Windows app on Linux if you use something called Wine. Okay, if you heard of Wine, that's what it does. It actually takes the Win32 and Win64 interface, is re-implemented on a Linux machine. Okay, so to the application, it looks like it's running on a Windows OS, although actually there's a layer that's emulating a Windows OS. It's really running on different operating system altogether. So this is called OS level virtualization, because you are now emulating an OS level interface. It's different from hardware virtualization, okay, where you mimic the hardware. Okay, or you could essentially do this at a library level or an application level, in which case you get application level virtualization. Okay, you essentially take one library, you emulate another library. Okay. So there are different levels of virtualization, and we'll talk about all of them. Okay. So essentially what you need to know is, you are trying at any layer, you are essentially taking that native interface and using it to emulate some other interface that you would like your application to see. Okay, so it could be emulating CPU instructions, emulating system calls, or library calls. Is that clear? Okay. So we'll start at the bottom. Okay, we are going to go into quite some detail on hardware virtualization. Okay. Next time we are actually going to talk a little bit about OS virtualization, and I'll mention application level virtualization in the passing, so you get some sense of what it does. Okay. But let me go through this in a little more detail, okay, what I just talked about. Okay. So there are, even within each of those layers, there are different types of virtualization. Okay. So let's talk about hardware virtualization for just a moment. Okay. You have something called emulation. Okay. In emulation, your virtual machine, which is actually a virtualization layer, is going to fully emulate a complete other machine. Okay. Every aspect of that other machine, whether it's the processor, whether it's the network interface card, it's the memory, it's the disk, it's fully emulated in software. This is a software implementation of an entire machine. Okay. This is called emulation or full emulation. Okay. There's an open source software called Box that does this. Okay. You can use Box to emulate a completely different architecture or a completely different machine and run that on a PC. Okay. So all aspects of your machine are actually emulated. There's another one called QEMU, which is a very popular virtualization layer that is used in many different projects. Okay. So that's emulation. There's something called full or native virtualization. In this case, your virtual machine or the virtualization layer doesn't actually emulate the whole machine, but it emulates enough of another interface of the machine for you to run an entire operating system on top of it. Okay. So now this is typically done when your emulated interface and the native interface are one and the same. That is why you can get away by not emulating the whole machine, because all you need to emulate are parts of the machine, because the rest are actually the same as what is provided by the hardware. Okay. So if interface A and interface B on the previous slide are one and the same, okay, they are actually using the native interface to provide the same implementation, you essentially get full or native virtualization. Okay. So you might ask, why would you take one interface and provide the same interface on top of the virtualization layer? What does this buy you? Why couldn't you run the application natively? Sorry, what did you say?
Like version control.
Version control. Can you elaborate a little bit?
Some software can only run the previous version of OS.
Okay. Some software, so we'll come back to your version control. I think that is actually at a different layer, but here we are talking about hardware virtualization. So you are basically emulating x86 on x86, Intel on Intel. Okay, both the interfaces are the same. What does this give you? Yes. Okay, so you can run two operating systems at the same time. Okay, if you run VirtualBox, has anybody? I'm sure you must have encountered VirtualBox, right? The VirtualBox gives you a software implementation of a Intel machine. It's implemented on an Intel machine. So it's emulating Intel on Intel. But what it gives you is it allows you the ability to run a whole different operating system inside that emulated machine. Okay? You can use this for things like testing, for development. Right? So you test a program, you don't want it to run on your native machine because it might crash the machine. But if it crashes your VM, you don't care. Your machine as a whole is still running, up and running. Right? So there are many reasons why you would run things in VirtualBox. The OS that runs inside that on that interface doesn't have to be the same as the underlying interface. So you can have a Linux box, you can run Windows inside the virtual machine, or you can have Windows, or you can run Mac OS X inside the virtual machine. So you can actually have two different OSs running on the same machine, which you would not be able to do normally. Okay? This is not like you have a dual boot where you boot one or the other. You are actually running two operating systems at the same time. One is running on the actual hardware, the other is running on the emulated CPU that's running inside the virtual machine. Okay? So that's the reason you want to do full or native virtualization, and there are many examples. There's VMware Workstation, there's Parallels, there's VirtualBox. They all do this. Okay? And this doesn't require you to do full emulation because you're emulating the same hardware, so you don't need to implement memory or disks and so on. It's the same family. Okay? You only essentially do enough to provide this illusion of a new OS, or the new machine rather. Okay? There's another technology called para-virtualization, which we will get to as well in a little more detail today. In this case, you are not actually simulating hardware at all, but you are using a modified interface that a special OS kernel needs to use in order to provide virtualization capability. Okay? In the previous two examples, you could run unmodified operating system. You could take stock Linux or stock Windows and just run it as it ran on a real machine inside a virtual machine. No need to change it at all. Okay? In para-virtualization, the OS has actually been modified specifically to support virtualization. Okay? And you can only run that special kernel because it doesn't need any special hardware support and things like that, as we will see. Okay? So you cannot run a stock OS on para-virtualized platforms. You actually have to run a special OS. But it then, once you run that, it gives you all the benefits of virtualization that we talked about. You can emulate one with the other and whatnot. Okay? So those are forms of hardware level virtualization. Okay? Then you have OS level virtualization, where you are taking one interface, one OS interface, and emulating another OS interface. Okay? So as was mentioned previously, there is notion of version control. Okay? Say you developed your application on Linux 4.2. Okay? In 4.3, maybe there were small changes in the OS interface. Okay? This might cause your application to break, or you might have to recompile it. Okay? But if your OS supports virtualization or OS level virtualization, you can essentially emulate an older version of the OS. So that you are emulating the same OS but an older version. Okay? That's what IBM did with their mainframes. Okay? Except that in their case the hardware also changed, not just the software. But you can think of a special case where only the software is changing but not the hardware. Okay? That is one example, okay, of where you would use it. Of course, you can emulate one OS interface using the other. As I said, example of Wine, which essentially implements the Win32 API. It's an open source project. Okay? You can download it on a Mac and you can run Windows applications without modifying them at all, okay, because it emulates the Windows API. Okay, so that's another example of OS level virtualization. Okay, there are many such examples. Okay, so if you use Docker, okay, Docker is the most popular form today of OS level virtualization. Okay, it's all essentially virtualizing. It gives you this notion of a container. Okay, containers are all OS level virtualization technologies, as opposed to VMs, which are actually hardware level virtualization technologies. So virtual machine, if somebody says virtual machine, they usually mean hardware level virtualization. If they say containers, if you have heard all of these terms, they usually mean OS level virtualization. And we'll get to all of these things if you haven't heard of them before. Okay, but before Docker came along, there are all these other technologies that predated it that they also did OS level virtualization. Okay. More than a decade ago, it started with Solaris containers, where you could essentially, that's the Sun's operating system, as a Unix OS, that allowed you to emulate any kernel version of Solaris using any other kernel version. So this was used for backward compatibility, the same way IBM was selling their mainframe using their virtualization layer. Okay. And then in BSD or something called BSD jails, that essentially gives you an OS level virtualization. It's basically a jail is a way to sandbox an application and make it look like it's running on a different OS interface. Okay. That is why they use the term jails. Okay. And then you have Linux vServers and Linux containers, which Linux containers are the basis for Docker. Docker actually uses, at least when it runs on Linux, it uses Linux containers. Okay. We'll get to all of this. All you need to know at this point is that this is a different level of virtualization than what we talked about before. Here you are emulating one OS interface using the other. Okay. And then your application level virtualization, where you are using one application library to emulate the other. Simplest example of this is Java, your Java virtual machine. Okay. It's essentially using, maybe it's written in C++, or it's using C libraries to expose essentially a JVM, which is an abstract machine. It's not any real machine at all, but it's an abstract implementation of a machine. Okay. And all Java code runs on JVMs. Right. So that's an example. Okay. There's Rosetta on Mac, which is also an example of OS level virtualization. So this was a technology that Apple came up with when they switched from PowerPC to using Intel for their hardware. At one point, all Macs used to use PowerPC processor, different processor family than x86 family. They were not compatible. But at some point, they switched to using Intel processors like all other PCs. Okay. At that point, everything that ran on old Macs would not run on a new one because the underlying hardware had changed. Okay. So their equivalent of what IBM did was to have this technology called Rosetta, which did binary translation. It took a PowerPC executable, okay, and it took assembly instructions written and compiled in PowerPC, and it dynamically translated them to x86 instruction and ran them natively. Okay. Completely transparent to the user. You could simply double click a PowerPC application, it would just start up and run on an x86 machine, and you wouldn't even know that there's translation happening, there's virtualization going on, all of that. So it was a very nice technology that they developed. It doesn't exist anymore because nobody has PowerPC OSs, but for a number of generations of Mac OS, this was still built in. Okay. You could actually still have old PowerPC applications and run them unmodified on x86 machines. Your question?
Does this impact the process speed?
Okay. Question is, does it impact process speed? The answer is yes. All forms of virtualization are going to impact performance because you are doing translation. Everything is just translation. Right? So your virtualization software is always going to impose an overhead. You will never run at native speeds when you are running on a virtualization layer. Okay. Especially if you do things like binary translation, you will get some slowdown. But if you do it well, you can actually, that slowdown is acceptable. Okay. So you won't get something that's so slow that it's unusable, but you will see that it won't run as fast as a native application. Okay. But that's true for every form of virtualization, not just this one. Okay. Yes.
For Rosetta, so why the translation not happen before the program is run?
Okay. Question is, in Rosetta, why can the translation not happen before it is run? There are many ways you could do the translation. They chose to do a runtime translation because you don't have to do anything to the application beforehand. If the user chooses to run it, you just do it on the fly. You could have gone in and done some things, but I think that is much harder. Doing static translation is much harder than doing binary runtime translation. Okay. Yes, question.
If I remember correctly, Rosetta was supposed to be like the temporary stopgap because at the same time you were supposed to be dual compiling.
Yes.
It was like for the developers who had that.
Yes. So I think as is being pointed out, at the time they did the switch, you could actually compile your code and have two binaries being part of the same application. This was called a universal binary, where the binary actually had a PowerPC executable and a x86 executable part of the same application. And depending on which machine you ran on, it would start one or the other. But if you actually had an old executable that was just PowerPC only, you had to use this technology to make it run on x86. There was no opposite. You couldn't take a native x86 and run on PowerPC. They did not do the opposite, okay, because they didn't expect people would migrate backwards. So that was the assumption that they made. But in any case, that's application level virtualization. Any questions on this so far? Okay, I am going to now go into some detail into hardware level virtualization. Okay, but we finished module 1, so we have a break. I am going to tell a story and then we will continue. Okay, the story is called Lion and the Rabbit. Okay, and the story goes as follows. There is a forest where there is a rabbit and the rabbit is typing, and the fox comes along and it asks the rabbit, what is it that you are doing? Okay, and the rabbit says, I am writing a thesis on how rabbits can eat foxes. Okay, and then the fox starts laughing and saying, that is absurd. We all know that foxes eat rabbits, not the other way around. And then the rabbit says, come with me, let me show you, and takes the fox into a cave. And then after a while, the rabbit comes out and there's no sign of the fox. Okay? And then the rabbit continues to work, and then a wolf comes along. Okay? And the same thing happens. The wolf asks, what is it that you're doing? And then the rabbit says, I'm working on a new chapter of my thesis. It says how rabbits can eat wolves. Okay? And the wolf says the same thing, that this cannot happen, this is absurd because rabbits don't eat wolves. And then the rabbit says, let me show you, and takes the wolf into a cave, and then there's no sign of the wolf. Okay? And then later on, going to the cave, there's a lion sitting there with a pile of bones. Okay? So the moral of the story is, first of all, the rabbit is a grad student, and then the lion is the advisor. And the real moral of the story is, it doesn't matter what thesis topic you pick, what matters is who your advisor is. Okay? All right, so we'll continue that story next time with the part 2, but for now we'll move on to module 2. Okay? So now that you are all alert again, we'll talk about types of hypervisor. So we are now going to do a deep dive into hardware virtualization. Okay? Try to understand how it works, what you need at the hardware level to make it work, and so on. Okay? So there are 2 types of hardware level virtualization that are very common. Okay? And they have some obscure names. They're just called type 1 and type 2. Okay? Just decided to number them, not give them any name, but let's not worry about that. Okay? So here's what a type 1 hypervisor is: the layer that is implementing virtualization. Okay? The hardware virtualization layer is typically called a hypervisor. In some papers, you'll also hear the term virtual machine monitor, VMM. Okay? So both mean the same thing. Okay? Here we'll call it a hypervisor. Okay? So type 1 hypervisor, essentially this is a picture that shows it. So when your machine starts, okay, there is no OS that's going to boot on it. Okay? Typically when you start your machine, your operating system boots up. Okay? When you're using type 1 virtualization, there's no OS at all. Okay? What boots is essentially a type 1 hypervisor. So the hypervisor takes the role of an OS kernel, and that's the software that's actually going to boot on raw hardware. So when you power on your machine, it's your type 1 hypervisor that's going to boot. So it is going to play the role of what a kernel would normally do in the virtualization context. Okay? Now this hypervisor can give you the abstraction of virtual machines. You will see that in this case there are 2 boxes. So there are 2 virtual machines running on this hypervisor. Okay, one virtual machine actually is running the Windows OS. The other virtual machine is running the Linux OS. So there are 2 operating systems running concurrently on 2 VMs on this hardware. Okay? Okay, and then there are applications that run on those operating systems. As you will see, there's Excel and Word and all of these things running on each of the operating system. Okay? So what type 1 hypervisor has allowed us to do is, first of all, you can run multiple operating systems in multiple virtual machines. Okay? And they could be different operating systems. Each OS, when it runs on a VM, to it looks like it is the only thing running on the machine. Okay? Because it doesn't know about the presence of either the hypervisor or other virtual machine. Okay? So when an OS normally boots up, it's the only thing that runs on the hardware, and it controls all the resources on that machine. The VM makes it look exactly the same. It's a full emulation of a machine. So the OS actually thinks that it's running on real hardware, and it looks like real hardware to it. Okay? Question?
Can you do further virtualization on top of it?
Okay, question is, can you do further virtualization? Answer is yes, but it's complicated. Okay, that's called nested virtualization, which we are not going to talk about in this course. But yes, you can actually virtualize inside the OS other operating system. So it's called nested. virtualization. Okay. So that's type 1. Okay. Now typically this is used in server world. Okay. Most likely you would not have encountered type 1 virtualization, okay, because when you boot up your machine, you boot up your normal operating system, is Windows or Mac. You are not booting a hypervisor and then running VMs on it. This is typically used in server. This is what is used on the cloud, okay, because they're essentially booting hypervisor, creating smaller VMs which they lease out as servers to customers, okay, or inside enterprises when you have servers. This is the kind of virtualization that you would normally use. Okay. And now on this other picture, you have the other kind of virtualization, which is called type 2 virtualization. Okay. In this case, okay, when your machine boots up, it actually boots a normal operating system. It could be Mac, Windows, Linux, whatever your OS is. Okay. And on top of that virtual operating system, you actually run a type 2 hypervisor. Okay. And that type 2 hypervisor also provides an emulation of hardware. It actually emulates let's say an PC or an x86 machine, and again you can run another operating system, okay, inside that virtual machine, and you can have more than one VM like you had here. There's no, although this only shows you one, you can run more than one. Okay. And the native OS that boots up is called the host operating system. The operating system that runs inside the VM is called a guest operating system. Okay. So there are two VMs running, two OSs running, one on top of the other. And then if you started a second VM, there would be a third one running there. Okay. So you have one host, you can have any number of guests. Okay. And inside the guest, you can run any arbitrary application. And the host and the guest don't have to be the same. You can run Windows on a Mac. Okay. In this case, Windows would be the guest. It's running inside a VM. Mac is your native operating system, it's the host OS. Okay. And you have, of course, host applications running as well. Okay. Now, if you have used any form of virtualization like VirtualBox, that's all type 2 virtualization. Okay. VMware Workstation, VirtualBox, Parallel, desktops, these are all examples of type 2 virtualization. Okay. Yes, your question.
For the first type, are the operating systems running concurrently, or can you just switch between them?
Okay. Question is, in the first one, do the operating systems run in parallel concurrently, and do you switch between them? So in this case, okay, the hypervisor is behaving like the actual operating system. It is actually scheduling VMs, not scheduling processes. Okay. So if you have only one core, it's going to give time slices to VM, just as a OS provided time slices to processes. It will run this VM for some time, then that OS and its application would run. It would run the other VM for some other time, and so on and so forth. So all the scheduling that an OS would do is actually done by the hypervisor, except that the hypervisor schedules that entire VM and then lets the OS do whatever it wants inside that VM. Okay. So that is how you are actually going to run this framework.
Your scheduling process, scheduling the guest OS as a process?
Yes. Question is, in type 2 hypervisors, is the guest OS being scheduled as a process? In type 2 hypervisors, the entire VM and the OS actually looks like a normal process to the native operating system. So this host operating system will take this entire box and treat it as a single application process. And there's another process here, there's another process here. It will use its normal CPU scheduler to time share them. If you have cores, you can run things in parallel, but essentially you are scheduling the whole hypervisor, VM, and whatnot. And when that time slice runs, then the guest OS is going to run, and it's going to schedule an actual process and whatnot. Right? So that's, you will have some level of nesting here. Yes, question.
So how can the hypervisor is built on the host operating system, but emulates the hardware?
Okay, question is, how is it running on the host operating system? It is emulating the x86 interface using another x86 interface, but it doesn't run natively on that x86 interface. It's actually using the operating system to take advantage of it. I'm going to go into details of how you implement it in 2 slides. Okay, so we'll have to get to that. That will answer your question. Any other questions here? Yes.
The distinguishing characteristic between a type 1 and a type 2 hypervisor is whether the hypervisor is actually like embedded into the kernel. I think of something like VMware ESX, where it actually runs like a really minimal Linux and like has other
Right.
components and other processes like a WAMP pipeline. So it's not like there are no processes running
Right. So an example of a type 1 hypervisor is indeed ESX, VMware's ESX hypervisor. So typically it acts as its own kernel. Okay, you can implement an entire kernel from scratch. You can take one and actually change it so that it's just designed for for virtualization. And in ESX, the early versions actually took Linux and used it, then they changed it to something else and whatnot. But yes, I mean this layer essentially plays the role of an OS kernel. It does whatever a kernel does, except that what it is scheduling are not normal processes, it's scheduling virtual machines. Okay? So that's the main difference. So it is a bare bones OS in some sense, but it is designed for virtualization. Yes, question?
I think you mentioned this, but I missed it. If you add another guest OS on Type 2 hypervisor, would you need another hypervisor along with it, or would it just follow?
Right. So question is, if you add another guest OS, would you need a hypervisor? So think of this hypervisor as a layer, just as you have a layer here. You can run multiple VMs on top of it. Okay? But from an OS's perspective, it looks like an independent process. So this guest OS 1 looks like process 1. Guest OS 2 looks like process 2. So the same code of that hypervisor is present in both processes. Okay, in that sense, you could think of them as distinct, but they're actually the same layer that is now present in two processes from an OS standpoint. Any other questions? Okay, so we are now going to get into a little more detail of how Type 1 hypervisor works and so on. Okay, for this we need to know a little bit about computer architecture, and I'm going to give you the necessary background that you need to know so you understand what may be going on. Okay. First of all, if you take any CPU that you can have on any machine, what you need to know is that that CPU can run in one of two modes, what is called user mode and kernel mode. Okay. It doesn't matter what the CPU is. It could be Intel CPU, it could be some other PowerPC CPU, it could be the CPU on your phone. It doesn't really matter. Most of these processors have two modes of operation, a user mode and a kernel mode. Okay. Now, what's the difference between these two modes? If you take the instructions that the processor supports, the entire set of instructions, okay, in kernel mode, you can run any instruction from that set. Okay. In user mode, you're only allowed to run a subset of those instructions. Okay. So what that means is, in kernel mode, you let whatever instruction the program wants, you let it execute, but in the user mode, you would not. Okay. The main thinking is, when the OS kernel runs, it's more trusted, so you let it do whatever it wants. But when a user process is executing, you actually then switch the CPU to user mode, so you let it only run a more limited set of instructions. Okay. So you might say, what are instructions that you shouldn't let a user process run? Okay. So think of the very simple example is the halt instruction. Okay. Every processor as halt is going to just shut down the processor. Okay. You don't want arbitrary processes to just issue halt, because if you did, then a process can just shut down the entire machine just by executing one instruction. You trust the OS to issue halt because maybe OS knows that the user actually wants to stop the machine, but you don't let an application process do it because it could do things maliciously. Okay. Memory management instruction, same thing. Okay. You don't let a process look at whatever memory address it wants. Okay. In that case, you could look at some other process's memory and try to steal things from that process's memory. Okay. So you want memory management instructions to be only executed by the operating system. So it only runs in kernel mode, not in user mode. In user mode, these instructions are disabled. You're not allowed to run them. Okay. This is true for every processor. Okay. It has at least two modes, what are called user and kernel mode. Okay. Now, in the Intel architectures, you generalize this and you have more than two modes, okay, starting from the most trusted mode to the least trusted mode. Okay. By definition, you at least need two. Okay. In Intel, in that small picture that is shown there, which just looks like concentric circle, there are actually 4 circles shown. Those are 4 modes. Okay. The innermost mode is called ring 0. That's your kernel mode. It's fully trusted. You allow everything. Okay. And you progressively let fewer and fewer instructions execute as you go to the outermost ring. In this case, the modes are called rings. That's the terminology used in Intel world. Okay. So ring 3, which is the outermost, is essentially our user mode. Ring 0, which is the innermost, is the kernel mode. Okay. In ring 3, you basically run user processes. In ring 0, you run the kernel. But there are intermediate mode where you have a little more trust then you trust an arbitrary process, but not as much trust as you would trust a kernel. Okay? And we are going to use this when we do virtualization. Okay? We'll run our hypervisor in ring 0, our guest OSs will run in the intermediate rings, and arbitrary user processes will run in the outermost rings. Okay? So that's how we are going to use this. Okay? But what you really need to know is there are these two modes, and then there are some things allowed in, everything is allowed in kernel mode, but some things are not allowed in user mode. Specifically, instructions that we are going to call sensitive instructions. Okay? I/O instructions, memory management, halt, all of these are not allowed in user mode. So we'll call them sensitive, only allowed in kernel mode. Okay? So far, so good? Okay. Now, there are also going to be some instructions in your instruction set family that produce interrupts or traps and things like that. Okay? I/O instructions are a good example. They create a trap. Okay? Whenever it runs, it creates a trap or an interrupt that basically requires you to go into an interrupt handler, and then you allow the device to perform its I/O. That's how I/O is implemented at a hardware level. Okay? There's interrupt handling involved. Okay? So we'll call any instruction that actually causes a trap to be a privileged instruction. It's an instruction that's going to cause a trap. A trap is a software interrupt. Okay, there are many instructions that are also going to cause interrupts that have nothing to do with user or kernel mode. They just happen to be instructions that actually trigger a trap. Okay? Now, the main thing I want to mention with all of that background is type 1 virtualization is only possible on those processors where the sensitive instructions are a subset of the privileged instruction, which means it's only possible on processors where every sensitive instruction also is going to result in a trap. Yeah, why we will see in just a moment, but first try to understand what I just said. So basically it says every instruction that's only allowed in kernel mode, which are our sensitive instructions, also actually trigger a trap. Only then are you going to be able to implement type 1 virtualization at all. Okay? Now you might say, why is this required? What is this hardware property? Okay, first thing it should tell you is that type 1 virtualization requires some specialized hardware support. In particular, you need that property to be true on your processor, otherwise you cannot implement it. Okay? Next question is, why do you need that property to be true? Okay? Now let's ask, how are we going to map all our software layers into our, these are called protection rings, those are our user mode and kernel mode and so on, okay, in type 1 hypervisor. Okay. So there are multiple software layers here. You have the hypervisor layer, you have an operating system, and your user processes. Okay. There are at least 3 types of things running here. Because type 1 hypervisor is the most trusted. That's the thing that is actually controlling all the resources. So we will run it in kernel mode. Okay. We will basically run it in ring 0. Okay. Now user processes that are running inside your on any OS are the least trusted. So we will run them in ring 3 or we will run them in user mode. So those 2 things are clear where to run. Okay. The question is, what level of trust are you going to give to that OS that is running on top of the type 1 hypervisor? Where would you, how much trust do you want to place in it? Okay, so you have only, in the canonical case, you have only 2 choices, your user mode and kernel mode. Okay? So you should ask, should you run that OS in kernel mode? Yes.
Well, presumably it's used to running on actual hardware where it has access to kernel.
Yes, normally it would run in kernel mode. That should be a given because it is a kernel. The question is, when you are virtualizing the machine, when it's virtualized, what mode would you run it? Would you like to run it in kernel mode or should it run in user mode? If those were the only 2 options. Yes.
You are running in user mode because the guest OS can be like, you can use a malicious page and you can probably that.
Okay. So the suggestion is, let's not trust it. Let's run it in user mode. Because if you run it in kernel mode, it has the same privilege as the hypervisor. It can go and actually corrupt some other operating system because they have full control of the machine. Okay? Your other operating systems running there as well. So you can let one OS go and trample another OS if there's a malicious OS. There's no sandboxing allowed at all if you actually give full privileges to that OS. In fact, it can go and trample over the type 1 hypervisor as well. So then you are saying let's run it in user mode. Let's not trust it at all. Okay, that's the other option. You had something to say? No, okay. Okay, so say you ran it in user mode, then you ask what happens. Okay. Now as far as that OS is concerned, it thinks it is actually running on real hardware. It doesn't know it's running in a virtualized machine. Okay. So it is going to try to control all the resources on that machine as if it was running on a real machine. So when the process starts, okay, and it says do this IO, okay, it's going to trigger an IO instruction. Okay. Normally that only runs in kernel mode. Okay, this OS is actually running in user mode. So if it tries to do IO on behalf of an application that's running on top of it, that would not be allowed. So that means that you can't even open a file on that machine if it's running on a virtual machine. Okay? So that clearly can't happen. Right? Basically, if you don't trust it at all, it cannot do things it would normally need to do in order for it to provide services to its application. It needs to do IO, it needs to allocate memory to its processes. All those things are disallowed in user mode because you only trust them to happen in kernel mode. But we said we don't trust that OS. Okay? So then the question is, how are you going to implement it? Okay, this is why that result is what it is. And the result said all sensitive instructions should also cause a trap, and only then can you implement type 1 virtualization. Okay? So now here is what is going to happen. We are going to run this OS in user mode. Okay? Let's say it tries to do an IO instruction or perform some memory management operation. Because it is in the CPU is in user mode, and you try to implement or execute rather a sensitive instruction, it is going to cause a trap. Okay? Trap is an interrupt. Whenever there is an interrupt, you are essentially going to go into the kernel, which in this case is the hypervisor. Okay? So the hypervisor will start running immediately. Okay? It will see that the guest OS tried to execute an instruction it is not allowed to execute, and it will say let me execute it for you, and it will go and execute whatever the OS was trying to do on behalf of the OS. Okay? So the hypervisor is providing services to the OS that the OS normally would perform on a real hardware, but in this case is not allowed to perform because we reduced its privilege level. We didn't allow it to do certain things that it would normally do. Okay? So every time your guest OS, which is now running in OS, well, that's not a guest OS, that's just an OS, is trying to execute a sensitive instruction, you are going to cause a trap. It will go into the hypervisor. The hypervisor will perform that operation for you. And that's the only way you can make it work. Okay? If you just ignore those instructions saying this is not allowed, so I'm not even going to let you run it, then the OS wouldn't be able to do all of the things it normally does. Okay? And in fact, Intel x86 until recently essentially ignored all sensitive instructions that were run in user mode. You could execute an instruction, it will just ignore it altogether. Okay? So if you try to do IO in user mode, you would be ignored. If you try to do memory management, you would ignore. Try to halt the machine, you are ignored. Okay? So what this also says is type 1 hypervisor, it was not possible to run it on Intel architectures until recently when they added extra support to specifically allow this result to be true on that architecture. Okay? So old versions of Intel architecture still cannot run things like ESX hypervisor that require this kind of feature. Okay? New ones do. So what did they do? Okay, they added this hardware feature which is called VT, which stands for Virtualization Technology, or SVM, which I think is called Software Virtual Machine in the AMD world. They broadly do the same thing. Okay? So by default, you are in user mode, you are going to ignore your sensitive instruction. That is what all old Intel processors did. But if you turn on VT, you can essentially create a bitmap which allows you to turn on bits for a specific instruction. And if the bit is set, when that instruction executes in user mode, it will create a trap. Okay? So you can take all your sensitive instruction and turn the bits on so there's 1 bit per instruction for every instruction. Okay? So your bit vector, so you can go and actually turn the bits on, and then for those instructions when they run in user mode, the CPU will actually result in a trap. Okay? And that only happens if you are turned on this VT technology on your processor. If it's off, it will behave like the old processor, in which case you can't actually run type 1 hypervisor. So it was implemented solely for virtualization, to enable virtualization. Yes, question?
So in general, you're saying that not all sensitive instructions are privileged.
Yes, I think these are just two different concepts. Okay, privileged instructions are simply, by definitions, the ones that cause traps, that really have nothing to do with what type of, whether it's user instruction, kernel instruction, doesn't matter. Okay, sensitive instructions by definition are the only ones that you are allowed to run in kernel mode. Yeah, our result says kernel mode instructions should also additionally cause a trap. Only then you can implement type 1 virtualization. And the reason is because when you have virtualization, those instructions will actually be run by the guest operating system in user mode. And you want the hypervisor to know that this is happening so it can take over. Okay? So I have a picture actually to show exactly this happening, which is here. So you will see that there is the hardware, there's type 1 hypervisor, there's a guest operating system. And whenever that guest OS, when the user process, let's say, make a system call, tries to do I/O, the guest OS is going to do its normal thing. It thinks it's running on real hardware. It will try to execute all of these kernel mode instructions. Okay? And now if you have VT turned on an x86 architecture, those instructions will also cause a trap when they run in user mode. Okay? And when they run, and that trap will actually cause, a trap is an interrupt. You should know that whenever there's an interrupt, you essentially go to the OS and run an interrupt handler which tries to handle that interrupt. So that will essentially cause the hypervisor to take over. That's the default behavior of any interrupt or trap handling. Okay, you essentially go to the OS, in this case that's the hypervisor really, there's no OS, and say you deal with this, something has happened. Okay? And then that hypervisor is going to say what happened and what instruction that OS want to run, and then it will execute it, saying let me run it for you because I can run it in kernel mode, although the guest OS cannot. Okay? So that's how you're actually virtualizing the processor in type 1 virtualization. Okay, is that clear? Okay, there's quite a bit of details of you need to know what architectural principles apply, what features you need, and then you can go and do all of this. Yes?
So if the guest OS is creating some, it wants to manage memory,
Yes.
does that cause a trap?
Okay.
Also, like it wants to manage other VMs memory.
Yeah. So question is, if the guest OS wants to manage its memory, will it cause a trap, and can it actually manage other VMs memory? So in this case, the answer to the first question is yes. If you're trying to manage memory, you're going to change some page tables, and as you will see in a few slides, that is actually going to cause a trap because you are not allowed to change them. You don't actually have control over memory. It's the hypervisor that's controlling memory. It's going to cause a trap, and the hypervisor will make those changes for you. But one VM in this case is not allowed control of memory belonging to another VM.
Yeah, I mean, like the hypervisor is going to decide you cannot control other VMs.
Okay, it's not. So question is, does the hypervisor decide what you control? Actually, memory management is implemented in hardware in most cases. Okay, basically when you try to access some memory address that do not belong to your legal address space, you are not going to be allowed to do it by hardware because you don't do this in software. You do it in hardware because you don't want performance slowdown. So that's actually a hardware feature that most are. So this is the same way one process cannot access another process's memory. You use the same feature to prevent one OS from accessing another OS or another VM's memory. Okay, yes, question.
Does that mean you're saying that in type 1 hypervisors, every operating system thinks that, because it thinks that it's the only one, it can see all the resources that are using?
Okay, question is, since in type 1 hypervisor, does the guest OS see all the resources that it would normally see? So what happens is the type 1 hypervisor is going to allocate some resources to that VM. Okay? It will say, I have 16 GB of RAM. I'm going to allocate 4 GB to this VM. Okay? So that OS is only going to see 4 GB. It will think that the machine that's being emulated has 4 GB RAM. So it doesn't even know that underneath the machine has 16 or 32 GB RAM. So the same thing, you might say, of the 4 cores, I'm going to dedicate 1 core to this VM. So then the OS actually only sees one VM because that is what is emulated for you. So you are essentially constructing a slice of the hardware and allocating it to that virtual machine. So the guest OS doesn't even see the presence of other resources. Okay.
As a follow-up, when does it happen that it's trying to access some other operating system's memory because it doesn't know that it exists?
Right. So the question then is, when does it try to access another processor's memory? So it will not be allowed to, because it is limited in what it can see. That's the same thing that happens in a process actually. Your address space is limited by the OS, so you cannot even address some other address space, because you are addressing something that's virtual, not physical in this case. Okay. Yes.
So the bit vector that you talked about, the bit map, is that configured into the hypervisor, or is that something that?
Okay. This question is the bit vector configured in the hypervisor. No, it's actually that bit vector has to be configured on the processor. When you boot up, there's a set of settings in your BIOS. You have to turn it on, so it will turn it on the processor, and then the OS and the hypervisor just use it as is. Okay, so that's a hardware level feature, not a software feature. Okay, so let's move on to type 2 hypervisor. Okay, so how does this work? Okay, so now that things are different. Okay, now we actually have a third layer to worry about. I'm going to go back 2 slides. So there's your host operating system, which is what is booted on the machine. There's your type 2 hypervisor that actually runs as a normal process on the host operating system. And then there's a guest OS that also runs as a normal process on that type 2 hypervisor and the guest operating system. Okay. So in this case, your trusted entity is the host operating system, just because you booted Windows or Mac and whatnot. Okay. That's what you're going to trust. That's running on your bare metal. Okay. Your hypervisor is actually just a process, just as you had any other process running on that machine. Okay, and the guest OS is also another process. Well, it's the same process in this case, because part of the hypervisor is part of that guest OS. Okay. So it should be clear that even in this case, the guest OS is going to run in user mode. In fact, it is a user level process from the OS standpoint. Okay. It is the host operating system that is going to run in kernel mode. All guest operating systems are going to run in user mode. Okay. So you have the same problem you had here, which is that guest operating system thinks that it's running on real hardware. It is going to try to execute privileged instructions, or rather sensitive instructions, not privileged instructions. Okay. And then how should you handle them? Okay. In this case, we made sure they caused a trap, went into the hypervisor and dealt with it. What should we do in case of type 2 hypervisor? Okay. So type 2 hypervisor has no more control of the machine, unlike type 1 hypervisor. It's also a normal process, so it doesn't have any more privileges, so it can't do something for the guest OS anymore. Okay, unlike type 1 hypervisor. Okay. So what actually happens in type 2 hypervisors is binary translation. Okay. So your type 2 hypervisor, as it is executing OS code, okay, is actually scanning for instructions before that instruction executes. Every time it actually sees a sensitive assembly instruction, okay, it is actually going to replace it with a function call on the fly. This is happening while you are executing. It's just doing binary translation, because you're not allowed to execute those instructions. Right? So you are going to look for those instructions just before they're about to execute. You just go and change that instruction and insert a function call at that location. Okay, so you're going to implement, in this case, in case of VMware, which did this, you're essentially going to scan assembly code and you're going to implement, call a VMware procedure. That VMware procedure is going to emulate whatever that instruction wanted to do by making a system call to the actual operating system, which is the only one that can execute in kernel mode. Okay? So essentially every sensitive instruction on the fly is being changed to the function call that explicitly invokes the OS to execute that exact thing that instruction would do. Okay? So again, all of those instructions are going to go back to the OS, and the OS is going to perform that operation on behalf of the guest operating system and the hypervisor. But you are not using traps in this case. In this case, you are actually changing the instruction on the fly. Okay, which means that just before you execute any instruction, you got to scan it. So this is going to do on-the-fly binary translation. Okay? And then you are going to replace them with function calls, and those will invoke system calls at the OS, which will do the right thing for you. So for every sensitive instruction, you have to have a predefined function saying implement this using some real system calls and whatnot. Okay. So that is how you are going to actually, that's what VirtualBox would do or VMware would do and so on. Okay, that's the only way all of this is going to work. Okay, yes, question.
This is the primary reason why OSs on VirtualBox run typically much slower than actual because
Okay.
people can
Right. So the question is this a reason you are going to see a slowdown? This is indeed your virtualization overhead. This is the price you pay for virtualization. It is going to incur a significant performance penalty. Okay. So in things like VMware, you have code caches where you prefetch code, you scan them ahead of time in parallel while the OS is running, so that you have done this well before the instruction even hits the CPU, so you don't see slowdown, but occasionally you will see slowdown because there's extra overhead no matter what. You have to scan instructions and do all of that on the fly, and you can't do it and load the entire OS in memory. You don't have enough memory, so you have to keep caches and keep parts of the OS, keep doing this over and over. So there is going to be significant runtime performance overhead. Okay? That's the reason for you might see a slowdown. There's some other hand here. Okay. So type 2 virtualization is completely different in how it implements virtualization than type 1. Type 1 requires hardware feature. As you can imagine, type 2 needs no hardware features at all. Okay, because it is essentially not requiring that these instructions cause a trap. It's simply replacing them with functions that make system call. So in other words, type 2 virtualization can run on any processor without requiring special hardware support. Okay. This is why you have always been able to run things like VirtualBox, VMware Workstation on old machines, but not type 1 hypervisors. Okay, because that required explicit support from the processor. Yes.
These type 2 hypervisors will try and use like Intel VT if it's available, right?
Right. So questions, can type 2 hypervisors use Intel VT? Modern ones have started doing some extra optimization, but normally they wouldn't have to. Okay, but you will see that some of them say if you turn on VT, performance will improve because you can actually use some additional features. Yes.
In the type 1 hypervisor case, it's lying directly on the hardware resources, and we have the slicing happening in the system. So how is it in the type 2 case? What do the guest operating systems, if there's more than one, what do they think they have?
Right. So regardless of which type of virtualization you use, when you create your virtual machine, okay, you are going to have to allocate it resources. You are going to say this virtual machine should have so much megabytes or gigabytes of RAM, it should have so many cores, it should have so much disk space and whatnot. So this is going to be configured when you create the virtual machine. Okay? And then when you boot an OS on it, that machine is going to look like it has those resources, which is a subset of the resources you have. That is true whether you do type 1 or type 2 virtualization. Even in VirtualBox, when you create your VM, you are going to have to say, I will dedicate so much disk space, so many cores and whatnot. So that is what you are going to see. Okay? So that resources are basically allocated, and then that's what the guest OS is. Now, as far as the host OS is concerned, it still has to time slice across them. Okay? If you give dedicated cores, you can actually say, if I have 4 cores, I might give it 1 core dedicated. Then you basically, the CPU scheduler respects that. Otherwise, you are time shared with every other process that you have. Okay? Your memory allocation is going to be max memory allocation determined by whatever you allocated to the VM. Right? So that's basically some of that is done at configuration time, not at runtime. Right. The question is, if the host OS has a certain amount of RAM, what does the guest OS see? What part of the RAM? So the guest operating system, as I said, will get as much RAM as has been allocated by the user when they configured the virtual machine. If you have 16 GB of RAM here and you created that VM, it's at 4 GB goes to it, it will essentially boot on a machine that looks like it has 4 GB of RAM, independent of what's actually on the machine underneath. Okay? So it looks like it's booting on a PC with that much memory that was allocated to. Okay? Other question, yes?
Yeah, how does the type 2 hypervisor allocate, dedicate resources for the VM?
How does the type 2 hypervisor allocate dedicated resources? Typically, if type 2 hypervisor is just a process, okay, so it doesn't really get dedicated resources. Having said that, you can give maximum amount of resources. That doesn't mean that it has been dedicated. That is how much this underlying OS is allowed to give it. Okay? But you may not get that dedicated. In type 1, you can even dedicate those, because it's the hypervisor that controls resource allocation. Here the host OS controls it, so you don't have as much control. All you can say is this VM has this RAM, this much CPU, that's the max that you will get. You may not even get that, but the OS will think that it doesn't have more than that. Yes?
So if you're saying that it's only setting a maximum limit, would you run into a issue where the host OS processes are using memory that encroaches upon what's quote unquote allocated for the hypervisor?
Okay. So question is, if you allocate a certain amount of max memory, okay, just taking memory as an example, can other processes encroach on that? Remember that max is not the same as min. Max doesn't mean you get that all the time. That means you cannot get more than that. Just because I allocated 4 GB of RAM here doesn't mean 4 GB are dedicated to it. It doesn't mean dedicated. That just means that the OS thinks it has 4 GB to play with. Okay, you can essentially have VM swapping happening. You might actually at any point have less RAM. Okay, but if you use it, the OS might give you more. Just as any other process which needs more memory, your heap size increases, you get more allocation. So it basically competes. So, but that's the max. Doesn't mean you have it all the time. Okay, that's all it means. Okay, yes.
Follow up to that. The type 2 hypervisor presumably runs in virtual memory, right?
Type 2 hypervisor does run as a user process in virtual memory, yes. Right, so it's like any other. So it can swap from disk and whatnot. So you can pretend like you had whatever was allocated, even though you don't have it. Okay. So I'm going to now talk about one more, and then we will actually probably run out of time. The last one is called para-virtualization. Okay. So para-virtualization was developed as a workaround for type 1 hypervisors that needed to run on old hardware, that did not have that hardware support, which said sensitive instruction should cause a trap. Okay. So if you want to run type 1 hypervisor on old hardware, the only way to do it is to use what is called para-virtualization. So how do you do it? Now in this case, you can no longer run your OS unmodified. Okay. Just as type 2 hypervisors actually went and scanned the code of the OS and replaced every sensitive instruction with a function call that was done at runtime, in para-virtualization, a human has actually gone and looked at the source code of the operating system and removed every single call to a sensitive instruction and replaced it with the hypercall. Okay. So that function call that got inserted on the fly by your type 2 hypervisor has been inserted manually by a programmer, kernel programmer, into a kernel. So this kernel is called a para-virtualized kernel. So you essentially gone and stripped out all of your sensitive instructions, which would have normally caused a trap in a normal type 1 hypervisor, and you replace them with function calls to the hypervisor. So you explicitly did what type 2 hypervisor is doing at runtime. Okay. So this gives you a specialized kernel that is explicitly designed to run on a type 1 hypervisor. You can't no longer run stock Windows because that doesn't work, but you can run a para-virtualized Windows where you've gone and made these modifications. Okay. So now your OS, guest OS has no more sensitive instruction. All of them have been changed into function calls into the hypervisor. These function calls are called hypercalls. Okay. So here is your old true virtualization where you do a trap. Here you have a para-virtualization where you essentially have modified Linux, which is making a function call, okay, through what is called a hypercall. Just as your system calls to operating systems, your hypercalls to hypervisors. Okay. Now, if you do this, you no longer need any hardware support, because now there are no sensitive instructions. Nothing is actually good. That OS is by definition not going to run anything that requires kernel mode support. Okay, you already gone and changed the OS explicitly to remove all of that. Okay, so this allows you to run essentially your the type 1 hypervisors on older hardware or even newer hardware for that matter. It just doesn't need any special hardware support to implement type 1 virtualization. Okay. So this is what OS designers did when they realized you cannot actually do it on older hardware. So let's change the OS. Okay. You can just go and remove all the instructions that are causing problems and make them into functional. That's what you're doing in type 2 anyway. That was a performance overhead. You could have done this on the fly here as well, by the way. But that's a high overhead, so they actually went and changed the code. Yes, your question.
Special OS that just for virtualization.
Yes, that's a special OS just for virtualization. Okay. Any other questions here? It's not going to run on normal hardware, as you can see, because there are no special instructions anymore. They are all function call. So you actually need a hypervisor to run this OS. Okay. So that is hypervisors and para-virtualization that actually give us the benefit, allows us to take benefit of older hardware. So we have 1 minute. So I'm going to just quickly run out. Since we run out of time, we'll do one more slide and then stop. So there was earlier a question of how is memory handled and how does memory allocation work and so on. So everything we talked about so far actually talks about virtualizing one resource on your machine, which was the CPU. Okay. Of course, a machine has other resources. You have memory, you have disk, you have network. All of those resources actually have to be virtualized because they are shared across multiple VMs, whether it's type 1 or type 2. Okay. So we'll talk a little bit about how do you virtualize memory as a resource. Okay. So in this case, you have the same problem as before. Okay. If your OS, which is a guest OS, is going to go and try to change the memory allocation of a process, that typically is a sensitive instruction because only the OS is allowed to do things like change page tables and whatnot. Guest processes are not allowed to do this. But our OS in type 1 world actually runs as a user process. It does not have those privileges. It still maintains page tables. It still thinks it owns the machine, that it can do whatever it wants, but it's not allowed to. Okay? So what we do here is essentially we take those page tables that are maintained in the OS. A page table is simply a table that tells you what memory is allocated to a process. Every process has a page table that tracks what memory is allocated to it. Okay? And changing values in the page table is a sensitive operation, only allowed in kernel mode. Okay? Otherwise, you could change your memory space and access some random memory location belonging to a different process. Okay? So this is only allowed by the OS. But in this case, OS is running in guest mode. So what we do is we first change the page table to be read only. So it can be read but not written to. That you can do by changing a memory content to be read only content. Okay? So when the OS tries to write to that page table, that's automatically going to create a trap because that's a write instruction to a read only memory page. Okay? That's an error for the hardware. Okay? So that's going to cause a trap. Okay? That trap will cause the hypervisor to run. Okay? The hypervisor knows that there is a page table in that memory page which it made read only, and then the OS is trying to write something to it. So then what it actually does is it maintains a second page table called a shadow page table. That's exactly a mirror of the original page table. It makes those changes in its actual page table. Okay? Then makes that change or reflects that change in the OS's page table. So essentially it is going to change the page table for you. But rather than requiring any special support, we just essentially rely on a feature that already exists on all processors, which is to make parts of memory read only. If you try to write to a read only region of memory, you are going to get a trap by definition. That is actually an error which you are going to handle inside the hypervisor. Okay? So this is a basic feature that you are going to use to essentially change page tables on behalf of the OS, okay, which does not have privileges to do it. Yes, question. Okay, question, is it only for type 1 hypervisor? Yes, this was designed for type 1 hypervisor, but even in the guest operating system, you would have to, type 2 hypervisor, excuse me, you would have to do this, but you would actually not do it this way. You would have scanned that instruction and said, there's a page table changing code here. We are actually going to replace it with a function that calls the real OS and makes it change the code. Right? So the same things apply in type 2, but you are going to do binary translation to achieve this. So you only have to do this in type 1. Is this clear? Okay. So we ran out of time, so let's stop here. We will continue on Friday. There's a special class on Friday. Okay, so make sure you come.